Hmm? Hello. We'll start in like 1 to 2 minutes. Alright. Good afternoon, everyone. Hopefully you guys had a good weekend. Uh, Today's lecture is basically going to be on the mathematical properties of impulses, which will capitalize on our last lecture, lecture 3 in particular, as to the special signals we observed. And those special signals, if we recap, were the unit impulse, the unit step, the ramp, and the sinusoid. So this lecture today focuses on only the impulse properties and how are they important to us as we continue towards moving forward within this course and for any applicable courses as well later on within the degree. So in particular, when you're dealing with the unit impulse or any impulse, the important part will always be the area underneath the impulse. We don't really care about the height or the shape, or we might care a little bit where it occurs in time, but it is always the area under the impulse that is always important. And if you remember the mathematical definition for this, it basically was where the unit impulse is going to be equal to 0 at time not equal 0, because it's basically represented this as an instant in time, and physically this does not exist, but mathematically it can exist. And then if you integrate the unit impulse with respect to certain limits, you basically get a resultant of 1, and this integral here, it represents our area under the impulse, where the limits here need to be real numbers and eta needs to be more than 0. We also observe that for a shifting property of the unit impulse here, this was important for when we started discussing the topic of sampling, as to how can we use the unit impulse and then shift it around accordingly with some arbitrary continuous time signal g of t, or in this case g of tau, and then how we can find the area underneath this in order to extract out a particular time instance of g of t. And in this case, because we shifted the unit impulse by t1 accordingly, when we do the integral part here with the continuous time signal g of t, and in this case for the integration will be g of tau, and we multiply it by our unit impulse, which is shifted by t1, and we conduct the area by this integral operation, this effectively allows us mathematically to obtain the instantaneous value of g of t at t1. So, just to recap a little bit, our unit impulse here was basically represented as delta of t, and this basically was a straight line here at t equals 0. And for our purposes within this course, we assume that for the unit impulse, the keyword being unit, it always has a magnitude of 1. So this will be a height here of 1. And we can shift this unit impulse onto the positive time axis or the negative time axis accordingly by using delta of t minus tau, where tau in this case is going to be minus 4. As we can see here, because we have t minus 4, this means we shift 4 units towards the right. And to give you an indicator of this, if it's t minus tau, we shift to the right. If it's t plus tau, we shift to the left. The minus here indicates that the signal is delayed by how many seconds, or how many units of time, in this case 4. And if it's plus that unit, in this case, let's say if it was plus 4, it means that it is advanced in time, so that way it goes towards the left, and as such, it occurs earlier in time accordingly. So example here shows us an indication of where the unit impulse or impulse signal is shifted towards the left. And in this case, it is t plus tau, where tau is equal to 3. And as such, we shift 3 units towards the left instead. So just recapping, the impulses will move to the left if tau is more than 0. And if it will move to the right if tau is less than 0. Oops, that's wrong. I need to correct that slide. So this here should be if tau less than 0. This here should be if tau is more than 0. Oh wait, I had it correct. Oops. Yeah, I had it correct. My mistake. Let's go back one. Where is this? That's correct. If I just go back one slide. Right, yeah, that's correct. Okay, so what's on the slide here is correct. So, impulses will move towards the left accordingly once tau is more than 0. And impulses will move to the right if tau is less than 0. Yeah, I mixed it up. I mixed them up accordingly, but just remember that on visually here is that because when tau is more than 0, it's an advance, and when tau is less than 0, it's a delay. And advances are towards the left, delays are towards the right. In doing the time shifting accordingly, the magnitude of the impulses are unaffected. All we just do is just physically just shift the impulses left and right. Yes, it's t minus tau. The minus tau means that there will be a negative value, so that means there will be a delay. And as of such, the impulse will move towards the right instead. So like in our case here, because it's t minus tau here, and minus tau here is minus 2.5. So t minus 2.5, that shifts towards the right. If it was t plus tau, it means it will shift towards the left instead. So in this case, like t plus 4, it goes towards the left by 4 units. Alright, so what we need to observe here is what happens when we start using impulses with different signals or with other impulses in particular. So for this example in particular, this slide here is going to be focusing on the Y1 signal, the Y2 signal, and the Y3 signal accordingly. And then the next slide will focus on the Y4, Y5, and Y6 signals. Now, X1, X2, and X3 are basically impulse signals with different magnitudes, and they occur at different time instances accordingly. The same is true for the X4 signal as well. Our z of t signal, on the other hand, is going to be a triangular form, which is described as a piecewise continuous signal, where for 0 to 2 in time, we have a rising edge of 3t. For 2 to 4 in time, we have a falling edge of minus 3t plus 12. And then for everywhere else in time, the signal just basically does not exist. So for our y1 signal here, because we have x1 and x3, x1 is basically 3 delta of t minus 0.5. And this basically means that because it's t minus 0.5, it occurs here at t equal to 0.5, and it has a magnitude here of 3. Similarly, our x3 signal here, it's 4 delta of t plus 1, so that means it occurs at t equal to negative 1 here on the time axis, and has a magnitude of 4. So when you have an addition of 2 or more impulses, you basically just draw the impulses accordingly on the graph, if you need to represent them visually, and you show each one in turn for an addition operation. Similarly, for our y of 2t signal here, our x of 1 and x of 4t, or on the other hand, both occur at t equal to 0.5 seconds. Because if we see here, this one is at t minus 0.5, and this one here is also at t minus 0.5. In the instance where 2 impulses occur at the same time instance, in this case t equals to 0.5 seconds, we basically just do the result of the magnitudes. So in this case, this was 3 here, and this was negative 1.5. So the end result will be 3 minus 1.5, giving us a resultant of 1.5. For our y3 of t signal, because this is x1 of t and z of t, this basically means that the addition of the two signals is if we just draw our z of t signal here accordingly, and we just map our impulse accordingly here for x1 of t signal. So addition of impulses, once they don't occur on the same time instance, that means you just draw them accordingly as if they are represented independently of each other. If they do occur at the same time instance, you want to take the resultant of the magnitudes in order to obtain the operation, as we saw here for our y of 2t signal. And if our impulse is added towards any arbitrary linear signal or polynomial signal and so forth, it basically just means draw the signal as is and then just draw the impulse accordingly as well. So are there any particular questions regarding the addition of impulses with themselves and with other arbitrary signals? Yeah, sure, I can explain the second diagram again. So for y of 2t signal here, it's basically the addition of the x1t of signal and the x4t signal. So x1 of t, if we watch the instance of where it occurs, it's at t minus 0.5. And our x4 of t signal also occurs at the same time instance, t minus 0.5. So that basically means they both occur at t equal to 0.5 seconds. Because they both occur at the same time instance, that basically means that what we need to do is just watch the magnitudes here and then add or minus them accordingly and just get the results, and that will be our resultant impulse here. So in this case, x1 of t has a magnitude of 3 and x4 of t here has a magnitude of negative 1.5. So we just basically say 3 plus minus 1.5, so that was going to be 3 minus 1.5, and we get a result of 1.5 here accordingly. So if you're adding two different types of signals, and if they don't occur at the same time instance, you just draw them accordingly on the graph. If they do occur at the same time instance, however, the result of that impulse is going to be the summation of all the magnitudes accordingly. And once you have the resultant magnitude, you just draw the resultant magnitude of that impulse there at the particular time instance. So if those two had occurred at the same time instant and there was 3 and positive 1.5 instead of 3 and negative 1.5, the resultant magnitude would be 4.5. Yes, that is correct. So yes, if this was here as positive 1.5, it will be 3 plus 1.5, and we've got another result of 4.5 here accordingly. Yeah, sure. Okay, so for our third diagram, this basically is going to be our x1 of t signal here plus our z of t signal. So our x1 of t signal here is basically an impulse that occurred at t equal 0.5 seconds with a magnitude of 3. But our z of t signal is basically going to be an arbitrary signal here that represents our triangular waveform. Now, for an instant like this, it just basically means that you just draw the signals accordingly on the graph. So we draw a z of t signal first to represent our triangular wave, because this is going to be the rising edge, which is going to be 3t. This is going to be our falling edge here, which is going to be minus 3t plus 12. And then the impulse, which is going to be x1 of t, we just draw that accordingly here as well, because this is just going to be an instantaneous value in time. So the addition of an impulse with an arbitrary signal is just that you draw the arbitrary signal and then you just draw the impulse accordingly. If the magnitudes were both negative 3.5 and negative 1.5, the resultant magnitude would just be minus 4.5. So in that case, our impulse will go downwards instead. So meaning upwards here. It will now just go down here. The axis here will just extend and I will indicate for negative 4.5. So I'm getting to the multiplication of signals on the next slide. Alright, so I think that basically clears up all the questions for the addition of impulses. Alright, let's go on to the multiplication of impulses. So, on this slide in particular, we're going to be watching our Y4, our Y5, and Y6 resultant signals, where Y4, Y5, and Y6 are multiplications of the impulses with themselves or with arbitrary signals accordingly. So let's watch our Y4 of t signal first. So our Y4 of t here is going to be our x1 of t signal multiplied by z of t. So x1 of t we know occurs at t equal 0.5 seconds because of the t minus 0.5 here. And we know it has a magnitude of 3. But what about our z of t signal here accordingly? So because we know that our impulse here for x1 of t occurs at t equal 0.5 seconds, that means we now need to know what is the instantaneous value of z of t at t equals 0.5 seconds. So we first observe the time range here for where t equals 0.5 seconds is actually going to be. And we can see that the resultant equation for z of t is going to be 3 of t. We then substitute in t equal to 0.5 into our z of t equation. So as of such, So as of such, this means that we now observe z of 0.5 is equal to 3 of 0.5, and that's going to be 1.5. And because we know the instantaneous value of z at 0.5 seconds, and we also know the magnitude of the impulse at t equal 0.5 seconds, it's just a multiplication of the magnitudes at this point. So y4 here of t would just be the magnitude of the impulse at t equal 0.5 seconds, which is 3, multiplied by our instantaneous value of z of t, which will give us a result of 4.5. And as a result, we just draw a resultant impulse here with the resultant magnitude from our calculation. In this case, the resultant magnitude here was 4.5. And it will be at this point here at t equals 0.5 seconds. So yes, it's basically just like sifting. A multiplication of an impulse with any arbitrary signal will basically allow you to sift the value out. But if there are magnitudes involved, you just need to make sure that you multiply the magnitudes accordingly for that particular time instance. So let's watch our example here for a wire 5 signal, which basically illustrates the same thing accordingly as well, but now we're going to end up with a resultant negative impulse instead of a positive impulse as we saw here for a wire 4 signal. So a wire 5 signal here was x2 of t multiplied by z of t. Now x2 of t has a negative magnitude of negative 0.5. But it occurs here at time equals 2 seconds. And we know because it's multiplying with our z of t signal here, we need to make sure, okay, what's going to be our resultant equation for time equals 2 seconds? Now, we see here that this is for 0 less than t, but t is less than 2. So 2 is not included here, so we can't use this 3 of t signal. But we can see on the following line, 2 is included here, because it's 2 less than and equal to t. So we use our resultant equation here, which is minus 3t plus 12. Because we know that we're observing the impulse at t equals 2 seconds, we substitute t equals 2 inside our z of t equation here. That means we'll get minus 3 by 2, which is going to be minus 6, plus 12, which gives us a resultant of 6. But however, because the resultant of 6 here, whoops, I should probably write this out for anybody who's following. I'll erase the previous work in here. It's being recorded anyhow for the video, so you guys can see it when you're watching it later. So basically, in this case, we know that z of 2 will be minus 3 by 2 plus 12, which gives us a result of 6. And then we also know that our x of 2t signal occurred at t equals 2 seconds, yes, but had a magnitude of negative 0.5. And because we are multiplying, that means it's going to be y5 of t is going to be our negative impulse magnitude for x2 of t, which is negative 0.5, multiplied by instantaneous value of z of t at 2 seconds. As a result, we'll get minus 3. So our end result here is basically a negative impulse at t equals 2 seconds, but with a magnitude here of minus 3 from our calculation. Now, funnily enough, let's actually watch the y of 6t signal here. This is a multiplication of x of 3t by z of t. Now, x of 3t occurs at t plus 1 and has a magnitude of 4. And we know that our z of t signal here exists for 0 to 4 in terms of time. But because this is t plus 1, this impulse occurs at t equals to negative 1. And because it occurs at t equals to negative 1, this impulse never intersects with our z of t signal. And because it never intersects, that basically means that there will be no result. So our end result here is just going to be 0. So an important property for multiplication of impulse signals with any arbitrary signal is that the impulse must intersect with the existence of the arbitrary signal. If it does not intersect with the arbitrary signal, there will be no result, i.e. the result is just going to be 0. As we can see here for a case of the y of 6t signal. So are there any particular questions regarding the multiplication of impulse signals with arbitrary signals? Yeah, sure. So, for you to have a result from multiplication of an impulse signal with an arbitrary signal, the impulse must intersect with the arbitrary signal for where the arbitrary signal exists. So basically, if we watch this mathematically, that means that the z of t signal here exists in between t of 0 to t of 4. But for everywhere else in time, it's just going to be 0. Our x of 3t signal here occurs at t equal to -1, because this is t plus 1. That means the impulse here will actually be on the left-hand side of the axis. Excuse me. Right. So, because it occurs on the left-hand side of the axis here, and we know the magnitude here is 4, for t equals -1 for the z of t signal, that basically is just going to be 0. So the end result is just going to be 4 by 0, which gives us 0. So we don't need to go and do all of this to prove this mathematically. It basically just means that once the impulse intersects with the arbitrary signal for where it exists, there will be a result. But if it does not intersect, it basically means that the end result is just going to be 0. Hopefully that answers the question that you had. Alright. Well, if anyone has any other questions, I'll come back to the slide accordingly. Alright. So, an impulse train, which is also referred to as a comb function, is basically just a series of impulses which are spread by capital T, where capital T, as we saw from our previous lecture, was our sampling time. Capital T, in this case, as we can see here in the equation, basically represents the distance or the time intervals for which our samples are took. So capital T here being our sampling time will always remain constant. So our impulse train is basically just a series of impulses where each impulse is spaced t seconds apart from each other, and it keeps on repeating towards an infinite value or for a finite value. The mathematical equation for an impulse train is given by the summation series here, which is basically P of t is equal to the summation series between n equals to some negative value to positive value of delta t minus n capital T. Now, impulse train is quite important because this actually gives you the basis for how you can actually sample any arbitrary continuous time signal. So what would be our outcome if we took an arbitrary continuous time signal here, x of t, and we multiply it by our impulse train here, p of t, to get our end result, which is going to be xp of t. So basically what happens here is that, let's say we had our arbitrary x of t signal here, and then we have our our unit impulse train here, where all the magnitudes here are 1, and they're spaced t seconds apart evenly. And we then multiply the two signals. This means that for every instance of these impulses, we effectively sift out the instantaneous value, for these particular times. So this comes like if we're basically sampling a continuous time signal using an impulse train. Now in particular, as t here spreads further apart, you get less samples accordingly from sampling the x of t time signal here. If t is spaced closer, it basically means you have more samples representing the x of t signal itself. The trade-off with this is that the more samples that you have, that means you need to have more memory to represent these samples. Because sampling basically means you're transforming the signal from continuous time to discretized time. So you're basically converting an analog signal into a digital signal. And in doing so, the higher the accuracy, that means you need to take more samples, and that means you require more memory. The lower the accuracy means you take less samples, and you require less memory accordingly. And in practical terms, when you're converting an analog signal to a digital signal, it always comes down to how much memory you will have. If you have a lot of memory, by all means, you can get really high accuracy. But you don't have enough memory, then you're going to have to figure out, okay, what is going to be my minimal accuracy that I need in order to get a correct representation of this signal. So basically, the impulse train here is used to sample any arbitrary continuous time signal and to obtain the discretized time version of it accordingly. And basically what this means is that for every impulse here, because the magnitude here is 1, once it multiplies accordingly with the x of t signal for these particular times, we basically just get the instantaneous values here accordingly for each one of these impulses. So the discrete time impulse is basically delta of n or delta of nt, and it basically just means it's 1 for n equals 0 and then 0 everywhere else for n not equal to 0. So it operates similarly to the continuous time impulse, but because it's discretized time, we basically just say it doesn't follow the continuous time mathematical properties where we saw delta of t was equal to 0 for t not equal 0, and then the area under the impulse was 1. But discretized time, it's basically just delta of n is just equal to 1 for n equals 0, and then for 0 for where n is not equal to 0. And you can shift around the discrete time impulse accordingly as well. For minus values, it will shift towards the right. For positive values, it will shift towards the left, and so forth. Now, the discrete time impulse is referred to as the unit sample or the unit pulse, and it's quite important that you realize that the unit sample is not a sample version of the continuous time impulse function. It is not that you sample the continuous time impulse function to get this. The unit sample exists independently of the continuous time impulse function. And basically, you can apply the same shifting and sifting properties that you saw for the continuous time impulse function to our unit sample or discretized time impulse, and you can manipulate signals accordingly as well, just as you did in continuous time for discretized time version. So as of such, if we had like an arbitrary discretized time signal here, where we had samples accordingly, and we needed to obtain a particular value. So let's say we wanted our x of 0's value here. That's just going to be x of 0 multiplied by delta of n. But if we wanted our x of 1 value here, that means, yes, we can just do x of 1, but in order to obtain the actual representation of it, we would have to shift our discretized time impulse in order to match the same instance at which it occurred. So in this case, we say delta of n minus 1 multiplied by x of 1. Similarly, if we went to the left-hand side, because it's x of minus 1, that means we don't have to multiply it by delta of n plus 1. And so forth, as you keep on going for when you're extracting out values from a discretized time signal. So it operates similarly to our continuous time signal for extraction of values. If you were sampling values, it's basically the same operation. You multiply by the x of whatever value that you want, and then you say delta n minus that value or n plus that value in order to extract out a particular value that you require. And basically, in doing so, we can abstract this into a mathematical formula to say if we don't want to extract out one value, we want to extract out a series of values. We can basically represent this as a summation series where we have k tending towards negative infinity to positive infinity, which can be replaced with set limits. And we just basically say x of k multiplied by delta of n minus k. And this basically represents our shifting property of the unit sample. So it's similar to our shifting property in continuous time, just that it is represented in discretized time here by this mathematical equation. Now, we need to pay attention in particular what happens when we start dealing with discontinuous time signals, or piecewise continuous signals, which they are more commonly referred to. So, let's say we had some arbitrary x of t signal here, which is going to be a piecewise continuous signal. So we have one representation of it here before a particular time, t1, and then we have a next representation of here, but after time equals to t1. And what happens in this case when we start doing operations? So we know basically the definition for a piecewise continuous function means that, yes, it's still continuous for all values of t, but there are going to be breaks in the signal accordingly for certain parts of the signal. So basically, these breaks occur in a finite amount, or a set time amount, you can say. But basically, you can count how many times the signal is broken accordingly to give us this piecewise continuous function. So a pulse train, for example, is a good example of a piecewise continuous function because it's on for a particular time and then it's off for a particular time. These vertical representations here basically indicates to us our transitions of the signal here, where the piecewise continuous parts exist. So on, off, and so forth as we keep on going. And we know because the signal keeps on repeating itself, we know how much times it can go up to. And we can represent this mathematically by some form of equation, but this actually just gives us the proof that this is a piecewise continuous signal. So in particular, what we want to know is that if we go back to differentiation by first principles, okay, let's go back one slide because we have a question. Countably infinite basically means that if the signal keeps on repeating itself, we know for which instances the signal is going to repeat. So, an example here of countably infinite is that the signal is basically periodic in nature. And we know for any set period, it's going to be on for a particular time and then off for a particular time. The reason why we say countably infinite is that the signal just keeps on going towards forever. But we know for one set period that the signal is on for this time and off for this time. So we can basically describe the behavior of the signal using one set period of the signal, and it will keep on repeating itself, will keep on existing accountably throughout the entire existence of the signal. In short, it makes like if you have an infinite signal, you basically describe the signal in a finite time period. And you know that for that finite time period, it's going to keep on repeating throughout the entire existence of the signal. Alright, so for differentiation by first principles, for any continuous time signal, x of t, we basically say that we take the difference of two x of t signal time points being separated by h here, and then we do the division here of h in order to obtain our end result for our differentiation. Because as we know from mathematics, differentiation basically gives us the gradient of a signal. And we know basically the gradient is the difference in y values here divided by the difference in x values. Once this limit of h tends towards 0 exists, that means we can actually solve for the differentiation by first principles. And then doing the first principles differentiation here, that's how we actually arrive to a dx of t dt signal accordingly. So differentiation exists once the signal is continuous for wherever you are differentiating. But however, for piecewise continuous signals, the differentiation needs to account for these discontinuous parts. So in particular, we'll be watching for when the signal is turned on here at t1, because before t1 it doesn't exist, and then after t1 is this x1 of t signal. When the signal jumps accordingly in between x1 of t and x2 of t at t2, and then when the signal is off for t3 after x of 2 has occurred, and then it's basically back to 0 after t3. So keep in mind, we need to pay attention to the jumps that occur at t1, t2, and t3 accordingly for where we actually represented this in a differential equation. So this signal basically can be represented by using the unit step accordingly, where we can say x of t here is basically x1 of t, for a difference in unit steps here between t1 and t2 for x1 of t, and then for x2 of t for a difference of unit steps in between t2 and t3. So at this point, some people might be a little bit confused as to why do we have a difference of unit steps. So I'm actually going to draw this out to explain it to you. Why do we have this in particular in our equation? So let's watch u of t plus t1. So because it's u of t plus t1, that means t1 is going to be on our left-hand side of our axis. And then if we do or draw our unit step for this, that means that before t1, the signal is going to be 0. But then at t1 and then after t1, we basically step up here and we have this here. So let's watch for u of t minus t2 and draw this unit step accordingly. So in this particular case, because it's u of t minus t2, that means t2 is going to be on the right hand side of our axis, because the signal is shifted towards the right. And if we draw a unit step accordingly, everything before t2 is going to be 0, and everything after t2 is going to be 1. So it's like this, then here, and then like this. And the magnitude here is just 1. So what happens when we take the difference of these signals? So let's actually observe these signals here visually to see what actually does happen. So we're basically going to be watching what occurs before T1, in between T1 and T2, and then after T2 accordingly. So let me just put T2 a little more closer to visually represent this for alignment purposes. Alright. So before T1 here, if we watch our sketches, we basically know that here was 0, and here was 0, and here was 0. So the difference between those is just going to be 0. Now after T1, but before T2, T1 here, or U of t plus T1 signal, is 1. But our U of t minus T2 signal here is 0. So our result here is going to be 1 minus 0, which is going to be 1. And then if we observe what happens here, but after T2, our U of t plus T1 signal here is 1. And our U of t minus T2 signal here is 1 as well. So our end result here is going to be 1 minus 1, which will just give us 0. So the difference between two unit steps here, accordingly, will give us a rectangular signal here with a magnitude of 1. And because we have this rectangular signal, represented by our difference in unit steps, with a magnitude of 1, when we multiply this rectangular signal here with a magnitude of 1 with our x of 1t signal here, this basically extracts out accordingly our x of 1t signal. So this just multiplies all the magnitudes here of x1 of t by 1. And then for everything outside of it, meaning everything before T1 and everything after T2, it just basically multiplies by 0. So you get an end result of 0. The rectangular signal here is important for extraction of a signal for particular time frames. And our time frame here is in between T1 and T2. Similarly, for the x of 2t signal, this basically means that our rectangular time frame here, or rectangular window, is in between T2 and T3. So this actually allows us to extract out our x of 2t signal here accordingly in between these two particular times. Now because we express our x of t signal here using our unit steps accordingly to get our rectangular frames or rectangular windows, when we move towards the differential of the signal, we can basically express this using the differential of the step function and the unit impulse together. The unit impulses here would be where we have our discontinuities, and our step functions would have been our u of t signals representing for where our time windows or rectangular windows existed for x1 of t and x2 of t accordingly. So as of such, when we have our first jump here, meaning for T1, because remember this, the x1 of t signal doesn't exist before T1, but then it exists at T1 and then further on. The unit impulse is going to be delta of t plus t1, because t1 is on the negative side of the x-axis. And the jump here is given by our instantaneous time value, where x1 of t1 positive is minus by x1 of t1 negative. So the t1 positive here and the t1 negative here represents the time instant for where the unit impulse moves from a magnitude of 0 to a magnitude of 1. This is just a mathematical representation. It's nothing fancy. All it just indicates is that vertical transition from 0 to 1. Our second jump here, when we watch this, is that, okay, we're now dealing with our x of 1 signal, so we actually can differentiate this accordingly normally by saying dx1 of t of dt, but then we have our discontinuity at t2. So we say delta of t minus t2, and then we just represent that discontinuity. So I'll go back one slide. This discontinuity here that occurred at t2, we need to represent this accordingly in our differential. So this will be at t2 positive and then at t2 negative to represent this change. So our equation here will be x2 t2 positive minus x1 t2 negative. And the reason for this being is that x2 t2 positive, x2 t2 positive is what happens at this point here. And then x1 t1 negative occurs at this point here. Because the signal exists for x1 here before t2, as you can say. So that will be t2 negative. T2 negative, yes. And then the signal exists for x2 of t at t2 positive. That's how you end up with this representation here. And then we continue on with our differential. We can differentiate for the x2 of t signal accordingly, giving us dx2t of dt. And then we do this for the t3 part, where we say delta of t minus t3, where we say x2 of t3 positive minus x2 of t3 negative, and so forth, when we're doing our differentiation. The important concept here is that in doing the differential of piecewise continuous signals, do not forget these transitions. And this will actually become very important when we start doing problem set 1 as to how actually do you represent these transitions when you're visually drawing these signals. So a good visual representation here is given by this figure. Because we had our signal not existing before T1 and then it exists at T1, this transition here, being our differential, needs to be represented by this impulse to show that there was a change for the signal to start. So that actually represents our first jump here. The dx1 of dt is if we just differentiated our x of 1 signal here accordingly. And then our second jump, which was delta of t minus t2 x2 t2 positive minus x1 t2 negative, represents our change here from our previous signal here to this signal here. So our previous signal here being x1 and our new signal here being x2. Because we moved from a higher magnitude here to a lower magnitude, the resultant impulse is going to be negative in nature. Because we're not going in a positive direction, meaning we're going from 0 towards a positive value. We're going in a downwards direction. So this is going from a higher magnitude to a lower magnitude. And as such, the direction of the impulse represents the direction of change. So that's why we end up with a negative impulse here being delta of t minus t2. We then differentiate for x of 2t signal accordingly as well. And then our last transition, where we had x of 2t ending basically towards 0. This actually is also a negative impulse here at t3, because we are dealing with a higher magnitude towards a lower magnitude. So this represents the direction of change, and the magnitude here is mapped accordingly to this point. So further explanation will go on towards this when we actually start doing the questions and problem set 1, and why it is that it's important that we map out these impulse changes for piecewise continuous signals. Alright, so that basically is the end of this lecture. And if there are any questions regarding the differential of piecewise continuous signals or anything else within the lecture, I'll take questions now accordingly. If not, we can end the lecture here, and we'll see if there are any questions at this point in time. Why exactly does a unit step represent gradients? I'm a little bit unsure as what you mean. So do you mean the unit impulse instead representing the change? Or do you mean like when you integrate the unit step, why do you get gradient? Okay, I know I asked 2 questions there, so I'm particular in response. If it's straight up, should it be a discontinuity? Oh, alright, okay, I understand. You're talking about a unit impulse. Alright. So, it is mathematically you're representing this change because in the physical world, these discontinuities actually are really sharp changes in the signal. And because we're dealing with instantaneous changes, it doesn't mean that the signal is, so to say, fully continuous, but because we're saying it's piecewise continuous, you need it to actually represent these impulse changes to define the piecewise continuous property of the signal. So the piecewise continuous parts of the signal basically means that the signal jumps from one value to another value at that particular time frame. And those jumps are basically represented by impulses. And the impulse basically represents, okay, the magnitude of the impulse, say, is this a positive change or is this a negative change accordingly. So it's just basically a mathematical concept that represents these jumps for instantaneous time values. That's all that it is. When you actually get to physical real-world signals, as of such, it's basically a really sharp change with a very sharp gradient. Because the gradient is not infinite, it will just be like some really high number. So when you do the differential, you basically just get whatever that gradient is at, like say like 1 million, 2 million, something like that, because the change actually is that fast. But because if we did the physical differentiation here, because it's a vertical change, the gradient is infinite, we can't actually just say it's infinite. We visually represent this using a unit impulse accordingly. Alright, so I'm actually watching the clock here and we're basically out of time. So if there are any further questions, feel free to leave comments in the video down below. Or you can also email me accordingly if you have any questions according to this. And like I said, we will get to this differential of piecewise continuous signals in particular when we start doing the problem set 1. And problem set 1 isn't up as yet, but it will be up probably by the end of this week or a little bit earlier. I will be doing that in particular on next week Tuesday's session. But for tomorrow's section, we'll be going towards lecture 5 and 6 accordingly. So I'll see you guys tomorrow at 1 PM. Until then, take care, be safe, and I'll see you guys at that time. Later.